At the end of September, our design studio held a workshop for two Seattle neighborhoods, Georgetown and South Park. We invited the community to share their thoughts and ideas on best practice prototypes that we had been working on as solutions and adaptations to climate change and sea level rise. We were able to make adjustments to the prototypes from the thoughts shared at the workshop, and we encourage any further comments from you. If you didn't know already, about 2 years ago, the government requested a report on climate change impacts on the United States. This report was over 800 pages long, and yet it stated the term sea level rise 432 times. Scientists point to several causes of sea level rise. One being oceans are absorbing over 90% of increased atmospheric heat associated with emissions from human activity. And like mercury in a thermometer, water expands as it warms up. Scientists also point to increased rates of melting glaciers and ice sheets. Not only is the sea level rising, but it is also becoming more contaminated. The oceans are currently absorbing carbon dioxide emitted into the atmosphere and are becoming more acidic as a result. This is an example of seashells formed in non-acidic ocean water versus acidified ocean water. Due to sea level rise, less land will be available for food production. Scientists say that by the end of the century, 2 times the amount of food we create would then be required. Thinking a little more locally, in the event of flooding due to sea level rise, food availability could become an issue for Georgetown and South Park, as these neighborhoods rely on food that is trucked in. So what have people done to adapt? They've begun to float. Here's an example of a biosphere in the port of Genoa that floats. People have been using these structures as greenhouses as well, like this one in Holland. This floating greenhouse was designed and built in Florence, Italy, and uses hydroponics to grow food. Here is the Rotterdam Floating Pavilion in Copenhagen. This volunteer project was designed and built within a year, which proves floating technologies are available and are being used around the world. In order to adapt to all of these problems, this best practice produces clean water, food, and energy. It creates symbiotic relationships between these resources. This means that mutual relationships are made in order to maximize production and efficiency. Here's how it works. Rainwater could help support annual residence water requirements, so the structure's roof captures rainwater while the interior collects condensation from the water below. The plants clean the rainwater, which is then pumped into the fish garden. Fish can be grown year-round in order to supplement local needs. Clean water is then returned to the water body. As for energy, this design can be fitted with several types of renewable energy sources. OTEC, or ocean thermal energy conversion, uses different temperatures in the water to create energy. And of course, there is solar and wind power. Looking at this sea level rise analysis, you can see how the sea level rise might affect this area and where local populations reside. This may help influence certain locations. This best practice would work. Moving on.
Sea level rise isn't just threatening Seattle, it's also threatening my hometown of Olympia. The design solutions brainstormed during this workshop will be able to stand as a model for cities all across the Puget Sound who will also be dealing with sea level rise in the upcoming years. Flexible floatable parks provide many important functions. They have the ability to absorb water back into the ground, clean water, and provide room for the river. The following slides illustrate the broad spectrum of floatable parks. This first example demonstrates how people can interact with the system while it holds extra water. These parks can make room for rising water levels, but they can also treat toxic water runoff from nearby roads. This illustration shows a river project in Hoboken, New Jersey. This is a great example of a space that collects and holds runoff and provides an area for recreation as well. In case of an emergency, the park allows high river water to flood the park before it inundates the city. Yeager Park in Olympia, Washington is a baseball park during the summer, but during the winter, when street runoff is maximum, the park turns into a holding area for runoff. I've seen the positive effects of this park in person, and it prevents the adjacent streets from flooding like they did in the past. Tanner Springs Park in Portland, Oregon is a unique park that continues to draw people in while providing ecosystem services to the area. This park collects and treats rain and stormwater while providing a functional social space that people enjoy. This CSO treatment pond was proposed in Georgetown and South Park as a strictly functional space. There would be a levee that, when breached, would provide room for the rising river. There would also be a series of pools filled with specific plants that treat combined sewer overflow to prevent backup and also clean pollution. The CSO pond prototype was improved upon during the workshop and was decided that it should be more accessible and greener. Air quality was also a hot topic during the workshop. With that information, modifications were made to the combined sewer overflow park model. Phytoremediation ponds were designed to be more naturalized and show more vegetation. Vegetation was also added in the larger basin to clean stormwater runoff. Recreational space was added so that people can interact with this park space. The room for the river was improved naturalized design with added vegetation. This section cut gives a more detailed look at the processes happening under the surface of a floodable CSO park. The phytoremediation ponds receive the combined sewer overflow to prevent it from backing up. The combined sewer overflow matter moves through the ponds, and plants remove the toxins from the sewage. Clean water that was previously CSO waste is reused elsewhere. This is the room for the river space. It holds the floodable water as the river rises during a flood event. In South Park and Georgetown, the main issue with combined sewer overflow is when it enters the river, it becomes unsafe for people to interact with the water space. But the problem is intensified in the case of a large storm event where sewage is not only entering the river but can be backed up by the hydraulic pressure created by a storm event, forcing sewage into people's homes. South Park and Georgetown are making progress, but there are still combined sewer overflows in the city. You also notice that South Park is part of a large floodplain and could possibly be affected by floods in the future. This makes it the perfect candidate for an amphibious home to deal with sewage and floods. An amphibious home rests on the ground for most of the time. During storm events or floods, the house will rise from its pad and rise with the tide. It's tethered to the ground somehow so it doesn't float away. In Lake Washington, there's this very similar concept happening. Purely floating houses live on the river with a buoyant chamber underneath that allows them to float on top of the lake. If you combine this process of floating with reclaiming and recycling sewage and gray water, you could potentially deal with floods in a different way. Gray water is lightly soiled water that is easily filtered and can be reused inside of the house. Black water is fecal biosolids that we flush down the toilet. Nobody thinks about it, but this is a very possible income source as it is basically fuel and energy being produced.
Now it's street canals. In our last presentation, using the application Kahoot, the question was asked, what would you do in a scenario where sea level rose? 1. Maintain the status quo with an emergency plan. 2. Transitioning toward embracing the living with water. Proactively planning for a future community relocation. Were the results displayed the most people would rather embrace water and live with it. In Georgetown and South Park, both neighborhoods are really diverse, contributing to better results. People want to stay where they call home. The thought of leaving or relocating just isn't the most popular choice. Cities that have embraced living with water, particularly with the canal system, are San Antonio. San Antonio has adapted to the major floodings that have occurred by integrating a canal, an idea that was also expressed in our last workshop as a possible integration within wide streets in both of the neighborhoods. Specifically in San Antonio, the city has seen great benefits from businesses not going bankrupt to the thriving wildlife. Copenhagen is another example of how communities are living with the canal, where people navigate easier and water is channeled through the city to avoid flooding. Here we have a rendering of a possible design idea of a canal system that was based on the last workshop and could be implemented in different streets to channel water to a possible treatment plant or help navigate people from neighborhood to neighborhood. The canal would divert water away from the river in areas of high flood, while also cleaning the water body. The Panama Canal is a study we looked at that uses locked gates and how water can be leveled to navigate through. This would also allow for water to be in the canal year long and through any season. Navigating through such canals can be easy using amphibious vehicles. They would help people move across water bodies, and it would also express, and they could also be used to navigate people to safety. Breaking down ideas of how a canal may look through the neighborhoods are such as having chambers on both sides of the water and on each side of the canal. Phytoremediation plants that can contribute to cleaning the water coming down. Microbiofuel cells that help produce electricity to contribute to water being moved through the canal. Piezoelectric sensors are placed within the canal and triggered by the movement of the water.
So the next prototype is the Floodable Blue-Green Street. The Floodable Blue-Green Street prototype was inspired by the two neighborhood vision plans that were created by the Seattle Parks Foundation and the Barker Landscape Architecture firm. And in this slide are some of the comments that were taken from the community members during the workshops that were creating the two vision plans. And when reading through the two documents, something that I noticed, a recurring desire that was shared in the vision plans from the community members was the improvement of safety and beauty in the two neighborhood streets in South Park and Georgetown. So the floodable street prototype incorporates traffic calming with increased vegetation, pedestrian pavers, rain gardens, and a centrally located hydroponic remediation bed. And these features simultaneously will tackle air pollution problems that are coming from the neighboring industrial areas. But in the event of a flood, the street along with the right phytoremediation bed will have the capability to lift, while excess water pools into the underground detention reservoir. And the water from the reservoir would be pumped into the floating hydroponic beds, where it would filter both the contaminants and the salt. So the implemented phytoremediation bed in this prototype is also a productive solution to treat the polluted water coming from the Duwamish as well as stormwater runoff. Phytoremediation is a low-cost green technology that uses plants to clean both soil and water. Certain species of plants have the power to take up pollutants through their roots and break them down, and then they would hold them in place in their stems and leaves, and later they can be harvested for biofuel production. For the past 3 decades, the following major departments, such as the USDA, USGS, U.S. Department of Energy, NASA, and many others, have been funding and conducting research on phytoremediation and its cleaning benefits in transforming bodies of water and land. These images are of the avenue, and it is an example of a hydroponic phytoremediation bed being used. They are located in Washington, D.C., and it's not implemented as a streetscape, but it's located on a rooftop, and it prevents 76,000 gallons of storm water a year from entering the DC combined sewer system. And here's just another image of the avenue with the phytoremediation hydroponic beds. And an idea that was brought up during the workshop was to utilize the underground reservoir presented in the floodable street prototype and use the reservoir as an underground parking garage, and then in the event of a flood have it transform into a reservoir where water would be pumped from the Duwamish. And now Matt will share a prototype that addresses what could be done with this extra stored water.
So here we will look at the prototype of a water treatment plant. First, looking at the case studies of the Croton Water Treatment Plant in Bronx, New York. This filtration plant currently filters 10% of the city's drinking water and has the capacity to do a lot more. During drought, it provides 30% of the city's water consumption. This functional water treatment plant is also a functional green space. The top of the building consists of a driving range and pathways around the site. Below the driving range is water storage, which also irrigates the planters around the building. The next case study looks at another water treatment plant in North Copenhagen, created by Henning Larsen Architects. This is also another functional green space combined with water treatment. The overall design focuses on energy production, recycling, and stormwater management. What this design does very well is it allows for visitors to learn about water treatment. Tunnels with glass facades allow people to look in and see how their community's water is being cleaned and reused. Here is a proposed prototype that obtains multiple uses. Before talking about the uses, here is the proposed location in South Park for the water filtration plant. And the location of the site was selected mainly by looking at soil conditions of South Park. The key component to this prototype is shown on the map, which is the landfill, which is the tan circle at the southern portion of South Park. The top of the building is a park design that incorporates a pathway system throughout the whole area. The bottom portion of the building is mass phytoremediation plants to filter contaminants in water, and test plots phytoremediation plants to figure out which toxins can be uptaked with which types of plants, and also added vegetation around the whole site as well. The upper portion of the park consists of a more traditional park layout. This area contains space for recreational activity, an amphitheater for events, and additional green space. Now looking at the section of the site, we can see how the water filtration plant functions and why it is meant to be placed on top of a landfill. The subsurface shows a landfill underneath and water storage to allow for the building to float. One use is by burning mass phytoremediation plants, which can be created into green concrete and used for sustainable design on the site. From the landfill, we can collect methane gas that can be burned to generate heat and eventually electricity. Biomass from the landfill can be used to create biofuels through a process known as hydrothermal liquefaction. This process converts waste by elevating temperatures and pressures to create a very valuable and expensive diesel fuel. Lastly, we can have heat exchange, which creates power and keeps the site running and functional. All these prototypes are meant to work together in a goal of reducing sea level rise. Many of the prototypes also have other positive effects on the two communities. And without the help of the participants at the workshop, this project and its results would not be the same. So we'd like to thank you for your time, and we hope you enjoyed our presentation.